Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we're going to start talking about how to use integrals to calculate volume. Up until this point, we've used integrals to calculate area underneath a curve, area between two curves. Today we begin our three-dimensional journey. So let's just look at this problem that we're given, then we'll kind of talk through it. It says show the work for finding the volume of a solid formed by square cross sections perpendicular to the x-axis. Okay, so we have two curves here. We have the curve y equals 6, and we have the curve y equals 4 times the natural log of 3 minus x. And what we're going to do is we're going to think about raising this area up out of the two-dimensional space and making it three-dimensional. And let me just kind of sketch what we're talking about here. It says we're using square cross sections. So what that means is we're going to have a bunch of cross sections. When we say a bunch, it's actually going to be an infinite amount. Oops. And actually just pause the video so you don't have to see me keep erasing and trying to give this a good bit of perspective so that you can really see what this shape is going to look like, what the solid is going to look like. But if I continue to draw these cross sections, well, we're going to get a solid that kind of looks like a little stool or kind of a pyramid with some curved edges, with the top cut off. You can kind of compare it to whatever real-world object you want, but I think we can see here what the solid's going to look like. And we're going to eventually figure out how to use integration to find the volume of this. But it's important to note here that, again, every single slice, right, the pink slice, the orange slice, the green slice, and any other slice that I draw in here, it's going to be a square. So essentially we have an infinite number of cross sections stacked on top of one another, and we're actually going to look at, can I find the volume of one cross section? If I come up with a formula for that, can I use integration to then, sum all of those cross sections together? And we're actually going to give these cross sections a little bit of depth. So let me draw that on here. So now you can see that these cross sections do indeed have a third dimension, a depth. But again, if I had an infinite number of these, we could stack them together to form the entire solid. Now, let's come up with a formula for the volume of just one of these. We'll think about the pink cross section for now. And then we'll talk about maybe how we can use integration to figure out the volume of the entire solid. But let's first start with the volume of just the pink slice. Well, volume is equal to length times width times height. Let's actually move this up here. Now we need to figure out what the length, the width, and the height of this pink slice is. Well, let's call this the length, call this the width, and we'll call this the height. And we do know that this is a square, so in this case, the length and the height are going to be the same. Well, what is that length? And you may want to come over and take a look at this perspective of the graph. Well, the length is going to be the distance, right? If we're looking down at that pink cross section, that's what the bottom looks like. The length is the distance between the red curve, y equals 6, and the blue curve, y equals 4 times the natural log of 3 minus x. Well, to find that distance, we're going to take the difference of the two functions. So we're going to get 6 minus the entire function of the blue curve, so 4 times the natural log of 3 minus x. That would be the length. Now, because this is a square, we know that the height is the same. So you could write this out again, but I think the easier way to do this would just be to square that quantity. Right now we've covered the length and the height. We just have to think about what the width would be. Well, the width of these cross sections we want to make that infinitely thin, right? Because to get the best estimate, we want an infinite amount of these cross sections. It's kind of like when we found the area between two curves, right? So actually, let me go back here. I'll use this graph for reference. Right, when we first looked at estimating the area between two curves or estimating the area underneath a curve, right, we used rectangles to do that. And we'll just talk about the area underneath the blue curve here, actually. We won't even think about the red curve. So we had a bunch of different Riemann sums we could do. And we could kind of choose how many rectangles we wanted to use, right? So if I use 5 rectangles, this would actually be a right Riemann sum. It would be a decent estimate, but you can certainly see that there's a lot of area, between the rectangles and the curve that we wouldn't be counting. Well, what if we started to use a larger number of rectangles? Right? All of a sudden, the estimate becomes much, much better. Right? There's far less area that's not being accounted for. Right? The area of all of the rectangles is much closer to the area or the total area underneath the blue curve. And we could keep going, right? We could put 100 rectangles underneath and the estimate's going to be even closer. But the idea was when we did the area under a curve, we actually wanted to make these rectangles we wanted them to have a width that was as small as possible. And it's actually called an infinitesimal. What that was just our dx. Now, if you think back to how we found the actual area under this blue curve, right, we had the formula area is equal to the integral. In this case, it would be from 0 to 2. Times the but of the function, so 4 times the natural log of 3 minus x. Now, this part right here, well, that represents the height of those rectangles, right? It represents the distance from the function to the x-axis. The width of the rectangles, that was actually our dx. Right, so we had height times width, and then to sum all of those rectangles together, we did the integral over, in this case, we would have the interval 0 to 2. So the same idea is being applied when we're looking at volume. We need to find the volume of what one of the cross sections would be. Well, in this case, we have these square prisms, right, with a length, height, and width. We know the length and the height. Our width ends up being that dx part. Right, so now this represents, and I'll just write this again, length times height. This would be our width. Now this represents the volume of one cross section. Well, if I want to sum all of these cross sections together so that I get the entire volume of the solid, I'm just going to use my integral. So let me put this over here to the right. The volume of this entire solid would be the integral from 0 to 2 of 6 minus 4 times the natural log of 3 minus x dx. So we're integrating over the volume formula for one of these cross sections. Hopefully you see the connection there between how we set up an integral to find the area underneath a curve, and now we're setting up an integral to find the volume of this solid being formed by these cross sections, which are essentially just being raised up out of the two-dimensional surface. The good news is that when we get to this point, we can just jump straight to a calculator. This would not be something on the non-calculator section. Trying to evaluate this integral would be pretty difficult by hand. And as I'm looking at it, I see that I missed a square here. Otherwise, it actually wouldn't be that hard to evaluate if I didn't have that square. But having that there, again, not something they would make you do by hand. So we can just punch it right into a calculator. Pause the video, punch this into a calculator, and let's see what the volume of this solid turns out to be. Well, it turns out that this volume is approximately 26.666. All right, I know that was a bit of a lengthy explanation, but again, I wanted to make sure that we understood the connection there between what we were doing setting up integrals to find area and now what we're doing setting up integrals to find volume. Today, the only cross sections we're going to look at are squares and rectangles. We will get to some different types of cross sections, but that'll be in a later lesson. Today we'll keep it simple. Our cross sections will be squares or rectangles. Let's do 2 more practice problems on video. We're going to go down here to this one. It says let f of x equal e to the power of x over 4 and g of x equal 1. R is the region enclosed by the graphs of f and g and the line x equals 5. Oops. Now down below it says region R is the base of a solid. For each x value, the cross-section of the solid taken perpendicular to the x-axis is a rectangle whose base lies in R and whose height is x. So notice in our previous example, they didn't tell us what our height was. We kind of had to figure that out based on properties of a square. In this case, they just go right out and tell us that our height is going to be x. Let me draw this with a bit more perspective, just to help you kind of visualize what's going on. All right, so I just tilted the graph so it's going to be a little bit easier to see this 3-dimensional figure come up out of the surface. We are doing rectangles here with the base perpendicular to the x-axis. They could do an example where the base is perpendicular to the y-axis, and then you'll see we'll probably be writing our integrals in terms of y values rather than x values. But for this one, still perpendicular to the x. So let's just sketch in a couple of these cross sections. All right, so I drew in 3 of the cross sections, and then hopefully you can kind of see what's going on with this figure. It gets much taller as we move towards the positive x, the more positive x numbers. What we want to do is write an expression for the volume of one of these cross sections, and then just integrate from 0 to 5. 0 to 5. Well, the volume of one of these cross sections would be length times width times height. We know that the length is going to be the distance between the 2 functions, right? If I come over here and I just sketch what the bottom of the orange cross section is going to look like, we're going to see that rectangle. And the length of that rectangle is going to be the distance between the blue and the red, or the blue and the purple curve. So the blue curve is e to the power of x over 4. The purple curve is just y equals 1, or g of x equals 1, so we're just going to subtract 1. That is our length. I'm going to do our height next. The height, again, if these were squares, we would just square this quantity, but they're not squares. They tell us that the height is going to be x. They tell us the height of these cross sections or these rectangles are x, so we're multiplying by x. And the width is going to be our dx. So length times width times height. Again, if I want to sum up the volume of all of these cross sections, well, I'm just going to integrate. So this was the volume of one of the cross sections. If I want to find the volume of the whole solid, well, it's going to be equal to the integral from 0 to 5 of e to the power of x over 4 minus 1 times x dx. This would be another calculator problem, so we can just punch this right in. We are going to get the volume. Again, pause the video, you punch it in yourself just to make sure you can do it correctly. We are going to get a volume of approximately 17.461. All right, one more problem to do. I want to go through a problem where our cross sections are perpendicular to the y-axis. Both the ones we've done have been perpendicular to the x. I'm going to look at this one right here. This one is multiple choice, so we just have to identify the correct integral here. It says let R be the region enclosed by the functions y equals x over 2 plus 2, and the line y equals 5, as well as the y-axis. Region R is the base of a solid whose cross sections perpendicular to the y-axis are squares. I'm going to pause the video. We're going to do one more perspective drawing just so you can kind of see the difference between perpendicular to the x-axis, perpendicular to the y-axis, and then we'll talk about setting up an integral. All right, so that orange slice does go off the screen, but I think you get the idea. In this situation, right, these cross sections are perpendicular to the y rather than the x. So we're going to be integrating over an interval in terms of y, in this case from 2 to 5, rather than an interval in terms of x. So we need to think, if my interval is in terms of y, will that need to change anything else about the integral itself? And you could get a hint by looking at the answer choices, because you know one of those has to be correct, and there's something common about all of those that is not the same as our answers from the first two we've done so far. So what I'd like you to do is pause the video, see if you can build your own integral for the volume of this solid formed by these square prism cross sections, and then see if it matches one of your answer choices. Okay, so, and what I notice right away about these answer choices is that they're integrating with respect to y. So that means that the functions I'm using, they need to be in terms of y, not x. So right away, I see this function right here. I'm going to need to write that in terms of y instead of in terms of x. That's what I'm going to do first. I'm going to get y minus 2 is equal to x over 2. And then I get 2y minus 4 is equal to x. So now that's written in terms of y, which will make sense because I'm going to be differentiating with respect to y. Now, of course, my goal is to find the volume of one of these cross sections and then just integrate over the entire interval to find the volume of the whole solid. Well, the volume is going to be length times width times height because they are square prisms. I know my length is going to be the distance, right, between this blue line, and in this case, it's the y-axis. So I'm just going to be subtracting 2y minus 4. It's essentially minus 0 because we're looking at the line x equals 0, but you don't have to write that. You could just leave it as 2y minus 4. That is our length. Let's do our height next. Because this is a square, the height and the length are going to be the same. So I'm just squaring this, and this becomes length times height. And then my width is going to be that dy this time, right? Because I'm taking slices that are perpendicular to the y-axis, so the width is going to be some infinitesimal small change in y, not x. So there's my length, my height, and my width. Which means if I want to find the volume of the whole thing, it's going to be volume is equal to the integral over the interval 2 to 5 in terms of y. And then we're going to square the quantity 2y minus 4 and keep our dy. Hopefully that matches one of the answer choices. Let's come over here. we can automatically eliminate these two, right? That interval is in terms of x values, not y values, so we know those aren't going to be correct. The first one, we're squaring 3 minus y over 2. And it looks like for that one they did something with these two functions right here. It looks like they've replaced the x with the y in the first function and then subtracted that from 5. Either way, that's not going to be correct. B does match what we came up with, and that is the correct integral. Okay, we're going to pause the video there. You've seen an example of both types of problems that could come from this lesson. We're doing rectangles and squares for our cross sections, and we can either have them perpendicular to the x-axis or perpendicular to the y-axis. As always, enjoy the rest of your day, and we will look forward to seeing you next time.